Good afternoon. Thank you for attending this talk. Actually, I'm interested in these people that already know about Emmet and have installed, so raise your hands, please. So thank you for you three. So I want to get some data from the audience. How many of you guys have heard of the latest 0 days that happened on September? Raise your hands again. Some of you. How many of you were affected? Owned? We won't tell. This is not being recorded. Those are fake cameras. So, okay, some of them. So you may be wondering, okay, on September there were at least 3 0 days that I'm aware of. Apple's QuickTime, Adobe Acrobat Reader, parsing fonts containing sync records, and another one, Adobe Flash. So 0 day can happen to any vendor. And as you are probably wondering, 0 day exploitation can happen to anybody. So you may be wondering what you could do. There are not many ways to protect yourself from 0 days, right? From 0 days exploitation. Okay, you go to internet, you download a PDF. Is this going to contain an exploit? I'm going to get a new driver called rootkit.sys. Yes, no? Okay, so what can you do? Today we're going to present something called Emmet, the Enhanced Mitigation Experience Toolkit. This is not a definitive solution for this problem, but this is a tool that will help you mitigate the risks. I mean, browsing the internet, downloading PDFs, viewing Flash files, it contains a risk. So if you don't know about this tool, let's get into it. If you like it, download it. Let's see. With no further delay, let's get into this one.
So Furman and I are part of the MSRC Engineering React team. As Mike said earlier, we handle all incoming security issues that are found externally. These include things that are reported responsibly through Secure at Microsoft, as well as things that are posted to Millworm or Full Disclosure or BugTrack. If there's a security issue in a Microsoft product that's found externally and we become aware of it, we're the team that handles it from an engineering perspective. This includes making sure it gets fixed correctly, as well as making sure that all similar issues in the nearby code also get fixed, so that we, in an attempt to reduce the likelihood that we'll be issuing patches for the exact same area.
So yeah, my name is Fermin Serna. I'm a security software engineer in the MSRC engineering group also. My interests cover exploitation and mitigations in pretty common architectures such as x86 and also not so common ones. Parisk, Spark, ARM, all this cyberpunk-based stuff. So today we're going to present Emmet. It's going to be a brief introduction of the goals of Emmet, what we're trying to tackle, what is not designed for. Then later on we will present the previous version. The previous version was released 1 year ago, and we'll give some details, press pickup. We'll give some demos on how we stop with that particular version an exploit, and then we will go through deep into this version. This version was released last September. We'll go deep into details on the mitigations, the new mitigations that they are in place. We'll give some demos on 0 days exploitation, and later on we'll have a recap on what Emmet is and how you can benefit, how you can contact us. So this is going to be the agenda.
So the goal of Emmet, first and foremost, is to stop exploits. So software vulnerabilities are part of our everyday life. They're in pretty much every product you have, from Internet Explorer, Firefox, Opera, Adobe Reader, Adobe Flash, QuickTime. Everybody has vulnerabilities these days. So what happens when one of these vulnerabilities gets found before a fix is available and exploits start rolling in? Well, a lot of times you'll get mass exploitation. You'll get people really hurt, and there's no way to defend it. So Emmet is designed to help prevent that scenario, as well as scenarios where maybe a fix is available, but you haven't had a chance to deploy it yet. This could be, you're testing it with your line of business applications to make sure it doesn't break anything, or perhaps it's a new machine and you haven't had a chance to do it yet, or perhaps there's somebody on your network who's just lazy. So how does this help a customer? Well, there's a number of different ways that it helps. I mean, first and foremost, if you block an exploit, you can block somebody from getting owned. That's a huge win right there. But this includes things like targeted attacks. Suppose you have a line of business application that was developed decades ago. The developer may have long since left the company. There may be no way to rev the code. There may be no way to opt it into any of the more modern security protections. So Emmet is a way to allow a user or an admin to opt that tool or that line of business application into security mitigations. It also can help you protect against vulnerabilities that are not yet patched, as we've mentioned a couple of times, the zero-day vulnerabilities. How it does this is through a concept that I just mentioned called a security mitigation. So a security mitigation, simply put, is a technology designed to prevent an exploit from working. So some of these you may already be familiar with. We shipped one in XP called Data Execution Prevention, which marks certain memory pages as non-executable. Other mitigations, such as Structured Exception Handler Overwrite Protection, SEHOP, or Address Space Layout Randomization, were shipped with Vista and Server 2008 for the first time. So one thing that Emmet does is it brings a couple of these mitigations down level. So if a customer is stuck on XP because they have a line of business application that requires XP, well, they can bring those mitigations, SEHOP, down level to XP for that platform, for that product. We can apply it to pretty much any product you have out there. So it doesn't matter who wrote it, when it was written. It can be a Microsoft product, doesn't have to be a Microsoft product, it can be a third-party product, it can be an in-house product. We support all of them. So now I want to give you a demo with the previous version. This is version 1.0.2. This is blocking an exploit. The exploit that we're blocking is the Aurora exploit. If you were watching the news somewhere around was that February this last year, there was a big mess with Google getting owned by a vulnerability called, it was codenamed Aurora. It was a bug, Internet Explorer. There's no black helicopters. I don't hear any black helicopters, but I'm still not going to dig into who is behind it or why are they behind it. I don't really care. I just want to help protect people from getting owned. So I'm going to launch a video here. So this is an XP machine. So first thing I'm going to do is run a shortcut to the Emmet command line tool to show you that nothing is opted into Emmet. There's no list of processes being protected. Next thing I'm going to do is launch Internet Explorer, and we have a server running in the background that's hosting the Metasploit exploit for the Aurora issue. So here, when you visit it, it actually launches malware. This malware really doesn't do anything besides show you this little UI to try and scare you and show you that something bad could have happened. So here we'll say OK, and now we'll opt Emmet into the protections through this command line tool, and I'll list it again just to show you that it is opted in. You can see Internet Explorer in the list of Emmetized processes. Now this time when we go back to Internet Explorer, we bring it up, we'll visit the same Metasploit exploit, but rather than seeing the payload running, you'll see a crash. Now the reason you see this crash is that is actually two mitigations block this. We opted in Internet Explorer 6 into Data Execution Prevention. The original exploit for Aurora did not try to bypass DEP. And then we also have another mitigation unique to 1.0.2 called Heap Spray that blocked it further. So there were two techniques that would have blocked this exploit.
I was suspecting kind of an applause. It's okay, it's okay. No. The next one is going to be cooler.
So as I mentioned, this is codenamed Aurora. It was fixed by update we released, MS10.002. Emmet is not a reason it's not an alternate for patching. You should definitely apply the patch. The reason for this is some of these mitigation technologies could potentially be bypassed in the future. Exploit authors are constantly trying to rev their tools and their attack techniques in order to bypass whatever protections we put in place. So the ultimate solution is not to have the bug in your software, but if you're in a situation where that bug was there and you didn't have the fix, Emmet can help you stay safer. So in October 2009 is when we released the first version, 1.0.2. We had some pretty positive response from the press. SANS said this is not a substitute for having good code in the first place, but if you're stuck with a 10-year-old line of business app that's been killed or where the vendor's been killed or gone under, it's better than nothing. We had a similar comment from the Register mentioning how overflows are very common these days, and it's nice to have something to help defend them. The Australian Search also added a comment about zero-day vulnerabilities and how this can help you. And perhaps my favorite comment was from a security researcher named Jimmy Ray Purser. He was playing around with his structured exception handler attacks, and he tweeted a comment that said, it's blocked my attacks 10 out of 10 times. Is this really from Microsoft? And I don't know. I took that as kind of flattering that, here we are making a difference. So what's new in 2.0? The biggest change was a change in the UI, but before I get to that, there's also another change called, in the acronym. The first version was called the Enhanced Mitigation Evaluation Toolkit. The whole idea of it was to try out new mitigation techniques and technologies before we included them in the operating system. However, the response to the first version of the tool was overwhelming that people wanted to apply this to whatever applications they could just to stay protected. So we've renamed it because it's no longer an evaluation toolkit, but we wanted to stay with the same acronym. So the second E is now experience. It's the Enhanced Mitigation Experience Toolkit, because that didn't sound too horrible. So the first version, as I showed previously, it's a command line tool. You can add and remove applications to opt them in and out, and you can list the ones that have been configured. With a new version, we introduce a GUI. And with this GUI, we actually add some new functionality as well. So the top section, you'll see that it lists the mitigations that are supported by the operating system, and it allows you to see how are they configured, and if you click on the button, you can change their configuration. Below that, there's a list of the running processes, whether or not they've opted into DEP, and whether or not they've opted into Emmet. So I'm going to walk you through a little bit what the new UI looks like. It's an administrative application, so you'll get a prompt when you try and launch it. We do sign it, so you know who it's from. Here, here's the system status section that I mentioned, as well as the running processes. If you click on the Configure System button, it'll allow you to change the setting. Now, this only allows you to change the settings for mitigations that are supported by your operating system. So this is the kind of the default baseline policy. If you're on XP, you won't have SCHOP or ASLR, for example, SCHOP or ASLR. And we also include some profiles that allow you to set the recommended settings, or also choose a custom profile. And this is depending on your threshold for AppCompat issues. So I'm not going to apply any settings because I have to reboot my system. Here are the list of running processes. You currently see nothing's opted into Emmet. Now the reason for this is if you click on Configure Apps, I don't have anything configured to use Emmet right now. But I'm going to go ahead and click on Add. I'm going to navigate to Internet Explorer. It's in Program Files x86, iexplore.exe. And once you opt it in, it'll show you all the mitigations, and you can individually turn them on and off. I'm going to leave them all turned on. And now, if I launch Internet Explorer, it pops up. You go back, and if you click the refresh button, it'll refresh after 30 seconds on its own, but I'm not patient. You'll see running Emmet is checked. So it's opted into all those mitigations. It's an easy way to see that. And it'll give you a message when you close it if you need to restart applications or if you need to restart your system for them to become active. So since the new version came out, we also got some really good responses from the press, actually better responses than the first time. eWeek they quoted Forrester Research, and we were really pleased. They really liked what we were doing with this. ZDNet in the UK, a similar thing. Perhaps my favorite one, though, was when we got Slashdotted. So Slashdot's usually not a good thing for Microsoft. The Slashdot crowd typically doesn't like it, but this one wasn't so bad. And I read Slashdot.
The best one is to come.
Yeah, yeah. There's more coming later. But here you'll notice that it says Microsoft helps block the PDF 0-day. Well, we actually coordinated with Adobe, thanks to the help of Jeremy Dahlman and the Adobe security team, to announce in their official advisory that Emmet can be used as a workaround before the fix for the 0-day was out there. So we were really pleased to be able to do that, and we're very happy that the Adobe guys worked with us. I understand some Adobe guys are in the audience, so if you helped us with this, thank you.
Well, but the best one is this one.
Yeah, this is perhaps the best quote. So the guy who wrote the Metasploit exploit for this made a comment about Emmet as well. He said, "I agree. Use Emmet. Turn it up to the most secure setting you can, and it'll help keep you safe." So even the guys who are working against us credit us. I'm very happy with that.
Thank you, Joshua.
Yeah, thank you, Joshua. Yeah.
So we have seen what the new version of Emmet contains. It not only contains several a new UI. It's not only a new UI. It contains a totally re-engineered architecture and 2 new mitigations. In the previous version of Emmet, there was 4 mitigations, and on this one we added 2 more, mandatory ASLR and EAF, that stands for Export Address Table Filtering. Some of them, they are added to, I mean, for example, if you are using Windows 7 without Emmet, you don't have this. I mean, these are kind of an add-on, a new barrier of security, where you can put more barriers for attackers in order to compromise you. So the new architecture, new UI, 2 new mitigations. We are going to go deep into detail into the new mitigations right now. The first one is SCHOP. SCHOP, it was introduced in the OS in Vista Service Pack 1, I guess. It's disabled by default in the client SKUs, but enabled on the server SKUs. But Emmet is able to backport it even to XP. So it would be nice to have SCHOP on XP. So I'm going to try to explain what SCHOP is, what kind of problems we were trying to tackle. It's going to be a bit tough, so let's try.
And we'd also like to mention that this was developed by a gentleman by the name of Matt Miller. It was his brainchild, his work, so we'd like to thank him for doing
it. Yeah, thanks, Matt. So SCHOP, this is the stack, and on SCHOP usually lies a chain of structures. These structures, they are named exception registration records. This structure are 2 field structure. The first field is the next value, basically it's pointing to the next structure in the chain, and the second field is the handler value. Basically it's pointing to a function. I will later mention the reason for this chain. 3 things needs to be said for this chain. The first one is the operating system knows where the head of this chain is, because there is a pointer on the tab, the threat environment block, pointing to the first one. The second thing is the next value of the final exception registration record in the chain is pointing to FFFFFF. And the third thing is, what is this for? What is why the operating system? What's the reasoning for being there in the stack? So basically, when an exception happens in a program, let's say a read AV, a write AV, a division by 0, the operating system will go to the tab, grab the head of this chain, and it will go through all these exception registration records saying, okay, I'm going to call the handler, I'm going to grab the pointer from the handler, and I'm going to jump into it. Hey, did you handle this exception? Yes, no. If no, I'll go to the next exception registration record, and I will call to the next handler. So this is how it works without Emmet. Let's say that there is a buffer, and there is a buffer overflow in the stack, and we overwrite 1 or more exception registration records. At this point, we control the next value and the handler value. The handler value at this point is 0C, 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 0C. What Emmet is going to, well, actually 2 things. Go ahead, please. What the operating system is going to do is going to go to the first exception registration record since an event happened, and we're going to call the handler. Do you handle this exception? Yes, no. The first one is not going to handle this exception. So we go to the next one, and since the attacker controls the handler pointer, is going to jump into this address. This is how it works when we don't have SCHOP, the OS version of SCHOP, or Emmet's version of SCHOP. So what happens when Emmet is on? When Emmet is on, the first thing that happens is we introduce a new exception registration record at the end of the chain, and Emmet is going to validate before we iterate through all the exception registration records. It's going to validate if the chain is corrupted or not. Basically, if it ends with our special exception registration record. Since in this case the chain is totally corrupted, the final exception registration record is not pointing to ours. It's going to prevent the execution. It's going to prevent calling any handler, and it's going to prevent the attacker from controlling EIP and executing any malware or any shellcode. So yeah, this is how Emmet works. So we have a demo on this. This is a Windows 7 machine. This is Emmet. First of all, I'm going to show you some source code. This is a buffer overflow inside a try-catch. There is a 10 buffer with 16 bytes. And inside the try-catch, so there's going to be some exception handlers in the stack. We have an unbound string copy, so that's going to perform the overflow. Later on, we are going to force an exception because we're going to set the A character to an invalid in an invalid memory address. So first of all, I'm going to configure emmet for this program, so it's in temp. I will only leave the SHOP mitigation, so the other mitigation doesn't come in place. And I'm going to execute this. It's going to be in the temp, as we already said, and we're going to execute it with our favorite debugger, CDD. And we're going to supply a huge string in order to overflow the 16-bit characters. This string is going to overwrite one of the exception registration records. First of all, what I'm going to do is I'm going to show the chain. I mean, I'm not lying to you. The chain is there in the stack. As you can see here, in the TEP thread environment block, there is the first field is pointing to the head of the TEP. So we're going to iterate through this chain. We're going to show all this structure called exception registration record and two fields on the head, and we're going to go then to the next one. The first field is the next one, is pointing to the next one, and the second field is basically a function handler. Do you handle this exception? Yes, no, as we already said. So we're going to go to, in this case, kernel 32 exception handler 4. So we're going to go to the next one. Basically, what I'm going to show is the chain, and at the end of the chain is our magic exception handler. We'll go to the next one, as the next pointer is, and there's another one. In this case, the handler, well, the next one is pointing to another one, and the handler is pointing to NTDLL except handler 4. So let's go to the third one, and if I recall correctly, the third one is the emmet one. The next value, as I already said, is FFFFF. It's the latest one in the chain, and the handler should be pointing to emmet. This is the special value or the canary cookie that we're going to look for validating the chain. The handler is pointing to emmet DLL. This mitigation does not make sense if there is no ASLR in place. So we have a special trick for emmet. The image base is 10000, and it's always mapped even on XP, so it's going to be rebased always. And on this case, we continue, the overflow happened, the AV happened, so before calling into any handler, emmet through an vector exception handler validated the chain. The chain was corrupted, so we didn't go through any of the handlers. As you remember, one of the exception registration records was totally overflown, so the attacker controlled the next and the handler, but the operating system never fetched the corrupted handler and never called into it. So emmet prevented this attack in this case. The second mitigation that I'm going to present is dynamic dep. Probably this is obvious to you guys. Dep is a feature that relies on hardware support. Your processor must support this, and it's the operating system, the one that is that configures or take advantage of this mitigation. This is present since XP Service Pack 2. Basically, we enable this. Basically, what dep will do is will tell the processor, okay, this virtual memory is executable or not. So let's say that an attacker takes advantage of a vulnerability and it says, okay, I control the IP, where do I jump? If the next step on the exploit would be locate the cell code and jump into it. Since dep is off because of the system mitigation or because emmet wasn't configured for this application, the attacker can directly jump into the heap or the stack where the cell code is located, and since there is no executable bit, it will start executing the cell code. But when emmet is on, we are going to mark several pages as, well, basically we are going to enable dep for the system-wide. The operating system is going to mark only executable those pages that they are needed to. Let's say executables, or if you explicit call virtual alloc requesting memory that is executable. So in this case, the attacker again performs the exploit against any vulnerable program, and when it tries to jump into this into the shell code is still going to be there, but the virtual memory page for where the shell code is lying is not executable. It's going to, the processor itself, not even the OS, is going to raise an exception saying, no, you cannot execute from this point. So when emmet is on, this attack would fail.
All right, another mitigation I want to talk about is one called the heap spray mitigation or heap spray pre-allocation. So when an attacker takes control of a software vulnerability, one thing that typically needs to be done is they need to specify an address to execute shellcode at. This is shellcode that they've provided through some other means. Maybe it's a network packet, maybe it's a file. Now, one trick they have, though, is they don't know what memory address this shellcode is going to be placed at. They don't know if it's going to be at the same address each time. It's typically at a different address. So one thing they do is they'll oftentimes put data, often in the form of a script, that puts copies of the same data all over the address space. They'll make as many copies of their shellcode as they can. The idea is then when they exploit a vulnerability, they'll jump into an address that they've hard-coded, and odds are they've gotten their shellcode placed at that address. So the Emmet mitigation simply blocks the addresses that are most commonly used by exploits. It pre-allocates them and gives them no access so that nobody can run any code from there. If anybody tries to run code, an exception will be thrown and the process will crash. So here we've allocated that block of addresses. When the attacker tries to execute shellcode at those addresses, it gets blocked, process crashes. Now one thing you may be asking yourself is, well, couldn't they just use different addresses? This isn't that robust a mitigation. And this mitigation is not designed to be bulletproof. It's designed merely to block exploit techniques that are currently used. Not everybody's using Emmet. So today, you deploy this, most malware authors are going to be blocked by this. Pretty much every Metasploit exploit, the Adobe issue was blocked by this.
You can show some examples.
Yeah. So it's very, 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 very common. So by using these addresses, we're blocking the most common techniques. As they change, we'll change our techniques as well. We've also exposed the addresses in a registry key. So if a new 0-day comes out, that you can look at it and say it's using this address. You can add that so the processes block that address as well. And one thing I wanted to say, heap spray is a very common technique. It's used by pretty much every IE exploit out there. These are 3 samples from Millworm of exploits that you can download and use against Internet Explorer. It's very, very, very common. So I wanted to walk you through it real quick with a demo. So what I'm going to do is bring up Emmet and just show you that it's not configured for use with anything, so that you'll know that Emmet's not applied. Now I'm going to bring up command prompt, and in case you're wondering, yeah, I can't understand the title either. This is Furman's Spanish machine. I don't read Spanish, but he helped me. So now we're going to bring up calc32 in the debugger. We're going to let it run, and it'll pop up. Now, hopefully it doesn't have any vulnerabilities left in it, but we can't say that for sure. But anyway, we're going to drop one of the common heap spray addresses, 0C, 0C, 0C. Nothing's allocated there right now because there's no script, no attackers trying to exploit anything. But if we look at the memory protections on this, it's free. So if anything tries to ask for that memory address, if somebody allocates the memory, odds are they could get this address. So next thing we're going to do is we're going to opt in calculator into Emmet's protection. So it's system32 and then calc.exe. And now, once again, we'll turn off all the mitigations except for the memory mitigations. There's also a null page mitigation you'll see. The null page mitigation is the same as the heap spray mitigation, but just at the 0 page memory address. And now when we load it, you'll notice that the second DLL on this list here is Emmet DLL. Emmet's been injected in the process by an infrastructure called the appcompat shim infrastructure. That's what we use with version 2. And here, if we refresh it, you'll see calculator has been opted in. Now once we let it run and then we break into it, we'll look at 0C, 0C, 0C again. This still hasn't been allocated because it's fortunately not under attack. But this time, when we look at the memory protections, you won't see that they're free. You'll see that they're marked page no access. So the system is never going to give those pages out for anybody to use. So anybody tries to jump to them, we'll block them. Now we'll just quit. Now, the next mitigation I want to talk about is one called mandatory ASLR. So many of you are familiar with ASLR. If you went to the last ROP talk, you'll have heard about that. So a technique that, as I mentioned previously, attackers don't know where their shellcode is going to be located. So one technique they use is they'll jump into code in a module. This is the ROP technique. So the problem is if that address, if that module is at a known address, they can always jump into this known address, always get that code to run. So around Vista and Server 2008, we introduced something called address-based layout randomization. And the idea is that on every boot, modules get loaded in a different order. So an attacker can never predict where they're going to be at because they're always going to be at a different location. And this introduces basically app-compat for exploits. The problem is that for a module to be rebased at a different address, it has to opt in at compile time with a special flag called dynamic base. If it hasn't opted in with dynamic base, you get what you can see here with foo.dll. It's always going to be at the same address, so it's available for use with a ROP gadget. It can be used for an exploit. So what Emmet does with this mitigation is that it will pre-allocate that address where that module wants to be loaded at load time, and the loader will be forced to find a new home for it. And as the loader's logic works, it will always find a different address for it. So this actually happens not per boot, but per instance. So every time you run a process, the module will be at a different location. And that helps prevent ROP techniques from working. So here is a quick little video of mandatory ASLR in action. What we're going to do is actually show you nothing's opted in. Then we're going to open up a debugger again. And this time we're going to debug Acrobat Reader. So Acrobat Reader has a couple of modules that haven't opted into dynamic base. One of them was used in the latest 0-day. Another one is used, or another one that we're going to show you here. It's a different module. So we're going to start Acrobat Reader here real quick. It takes a second to start. And this module is not going to be used in any exploits. We're not giving away any secrets because it requires user interaction to load it. It's the linguistics DLL. So I wouldn't expect anybody to require a user to click edit dictionary before they get owned. So here if we look at the linguistics DLL and you look at its base address, it starts at this address here and it will always be at that address when it's loaded. So now what we're going to do is run Emmet again. And this time we're going to configure Acrobat Reader to be opted into the protections. And I guess that's the Spanish word for program files.
Hopefully.
Hopefully.
Not that good a problem.
Yeah. So now we're going to turn off all the mitigations except for the heap spray one, or sorry, the mandatory SLR one. So now we'll run it again. Let it go, and once again we have to do this edit dictionaries in order for the linguistics DLL to be loaded. Now when we go back and we look at the linguistics DLL, same command, you'll see that it's not at the same address. It's at 1db00000. Or wait, no, too many zeros, -1.
Closed.
So now we'll run it once more real quick. And just to show you that it is not predictable at all, it's yet at a different address. We have to do the edit dictionary thing just one more time to get it loaded. And now if we switch over, you'll see that this time, the other one was 1db, or bd.
DB.
db. All right. Well, this one, it's 1b9, so very different. So that's kind of how it works. It always forces it to a different address so somebody can't use it in their exploit.
So this mitigation is unique to the version 2.0. The next one that I'm going to present is also unique to the latest version. It's called Export Address Table Filtering, Access Filtering, also known as EAF. Before going deep into details into this mitigation, I'm going to give a little bit of background on how a shellcode works, how it locates a API. So you know you want to run some malware on your system, and you're going to I don't know call winesec cal.exe. So how the shellcode finds the winesec API? So basically, there are several structures that we're going to enumerate here: the TEP, PEP, LDR. And the shellcode will iterate through all of them, trying to gather information on where a specific module is in the virtual address. So let's go into the TEP. The TEP is always accessible. If you are running code, you basically do move EAX FS0, and you are getting data from the TEP. The TEP is the threat environment block. It's a per thread structure, contains data on the stack base, stack limit, the exception, registration chain, etc. So the interesting part here is that at offset 30 it is located the PEP. The PEP is a process environment block. So the shellcode will go to that offset, it will grab the offset to the PEP, and let's go to the PEP to see what it's going to get there. The interesting part of the PEP, the process environment block, is a per process structure. It contains a lot of information on the process, environment variables, I don't know, so many things. And it also contains something called the LDR structures. As you can see here, basically the LDR structures is a structure with 3 linked lists. Can you go to the next one, please? It's a module with 3 linked lists and some other information on the number of modules that it is loaded for the current process. So if the shellcode will go again to the PEP, and it will go through the LDR. Let's focus on the LDR, because the final goal for the shellcode is to find the address of an API. So it will go to one of these linked lists, and it will basically on this linked list you will find the image base of all the modules loaded in the process. At that specific address you will find the P file header. The P file header is fully documented, as you can see here, but the shellcode is interested in something called the image export directory. Basically we'll go through the DOS header, image file header, image optional header, and then it will end up in the export address table. This is commonly known as export address table. So this is a bigger picture of the export address table. It contains a lot of information on the number of functions that this module exports. Let's say that this is a food.dll, and in this case we export 3 functions, myfunc1, 2, and 3. So we need to focus here on the address of functions array, because in this array is the virtual address of the where the function is going to be located in this module. So the shellcode always has to go through this array to get the address of that function. In this case, we're interested in WinSX, so it will go to through this array in order to find the address. So a recap, here we have the shellcode. Through the FS register, it goes to the tab. Through the 30 offset, it goes to the PEP. On the PEP, we go to the LDR. And for all the modules listed in the LDR, we go through to the export address table, and we look for the specific API that we're looking for. In this case, we found it in the 3rd module. Again, we go through the address of names array, always. There is no, well, there are other options, but mostly the 99% of the shellcodes, they will go through this array. So how Emmet works on here? We take advantage of something called data breakpoints. And data breakpoints take advantage of debug registers. So basically the operating system can say, okay, raise an event whenever you access, read, write, or execute from or to this address. So basically we say, okay, whenever someone is trying to read, write, or execute from address of functions, let me know. We do this for kernel 32 and NTDLL, and basically the logic behind Emmet is, okay, someone is trying to access this array. Is CIP the program counter inside a module? Okay, probably it's a legit access. Let's allow it. Is this not EIP not inside a module? This is probably some weird stuff or a shellcode. Let's block it. If it is not inside the EIP, we crash the process basically. This mitigation is breaking 99.9. I don't want to fail on the 100% shellcodes that they are outside right now. Can be bypassed, but you need further development on the shellcodes. We're going to go to the demo. For this one, I'm going to show how to block a shellcode from Metasploit. It is going to start running the shellcode. This shellcode is going to pop up cal.exe. And basically we request some memory, some executable memory through virtualalloc. We copy the shellcode to this requested memory through memcopy, and then we jump into it. This, I mean, without Emmet, you will see cal.exe popping up. We'll see that Emmet is not configured for this sample program, and we will execute this program through GDB, or probably not through GDB. We will go to a temp directory. Basically, we are going to execute this program. It should pop up cal.exe. as we will see right now. It's there. So let's go back to Emmet. Let's configure Emmet for this test program. And again, we are going to stop the shell code while it is executing, because it's going to access this array of functions, and the shell code is not inside a model, and it's going to be stopped. We disable all the mitigations except of the EAF. And let's run again the shell code. As you can see, Emmet is running on this executable, and you should see a crash here. Okay, the shell code stopped running.
I think that's a crash.
Yeah, that's a crash. This is a generic shell code from Metasploit for WinSec cal.exe. Yeah, so this is the export address table filtering. It's only available in the latest version. So we're going to quickly present a demo on how we block the latest Adobe exploit. Basically, this exploit was taking advantage of a DLL that was located on a predictable mapping. We're going to use the Metasploit exploit for this one, thanks to Joshua Drake for this exploit and for his quote. We launch it. It's going to take a while because it hits sprays and it's a little bit slow. This is a VM, blah, blah. But it will eventually, you will see popping up cal.exe. Again, this exploit is a stack buffer overflow, but it takes advantage of a predictable mapping to bypass ASLR and dep. This exploit is going to be, okay, you see here cal.exe. Emmet is not in place. This exploit is kind of 100% reliable. But let's configure Emmet for this. This exploit, as I already said, takes advantage of a non-ASLR aware DLL. So there are particularly two mitigations that will block this one. First one is going to be mandatory ASLR. Whenever the Metasploit shell codes try to reuse gadgets, ROP gadgets, return-oriented programming gadgets, it will fail because the DLL is not going to be there. We pre-allocate the base, and the OS is going to put the DLL in some other place. And the second mitigation that is going to block this one is the export address table filtering. Even if mandatory ASLR is not there, and they successfully use the ROP gadgets, and they successfully place a shell code in an executable memory, and they point EIP into that memory, even at that point, the shell code is executing, we can block it. So let's try it again. It's going to take a while, and we'll see Adobe Acrobat Reader crashing, and so you should not see cal.exe popping up. Hopefully, take some time. The Metasploit developers. So I was expecting an applause on this one, sorry. Okay, yeah.
All right.
So you can see, this is not the latest version. Adobe patched this vulnerability some days or some weeks ago. So go patch your Adobe Acrobat Reader. That's it. So Emmet is a free tool. There is a risk there, outside there. 0 days. 0 days can happen to anyone. This is the best we can do right now. This is not a final solution. This is how to minimize the risk while you try to do your daily job. Visit our blog. We publish news on Emmet. We publish new versions. And we want to hear from you. Here is our email alias and email address. Let us know what you think.
Any feedback you have on Emmet, any requests, swytech@microsoft.com.
And again, special thanks to Matt Miller, Jeremy Dahlman, and the Adobe security team for...
Yeah. And one real quick shameless plug. We have a lot of openings in our group right now. So if you're interested, there's both technical and program management and marketing all over the place. Just careers.microsoft, search for trustworthy computing and security, and you'll find us.